Hello, welcome back with another question discussion. As you can see, this question mainly from gaseous state of matter. But if you carefully look at this question, it's not only from the gaseous state of matter. To analyze this question properly, other than the concepts in gaseous state of matter, you need some concepts in chemical calculation also. Mainly the limiting reagent part. Maybe you have heard about that limiting reagent. Maybe you know everything regarding limiting reagent. So as an example, let's say there are two reactants in the reaction and both of these two reactants are available at the beginning, means the number of moles of these two are given. But then you can't find out the amount of product formed without finding the limiting reagent, because based on the limiting reagent only you can predict the amount of product formed. Therefore, in this question, that's the problem. You have to find out the limiting reagent first. But to find out the limiting reagent first out of NO and O2, you need the number of moles of these two gases, initial moles of these two gases. Are they given directly? No, those are not given directly. But they have given some data to find out the number of moles of initial moles of these two gases. So what are the data available? The pressure given, volume given, temperature given. R is a constant, you know that one. So applying PV equals nRT, you can find out the initial moles of nitric oxide. Same thing can be done for oxygen also, the initial moles of oxygen. So that's the way we start the question. Thereafter, we can find out the limiting reagent. From that, we go to the product. Then we continue until we get the answer in this manner. Okay, then let's continue the discussion. Right. So according to the question, you are given a balanced chemical equation. So what is balanced chemical equation? It's about 2NO gas react with O2 gas to give 2NO2. This is what you are given. But here, this is quite a special because this 2NO2 completely converted into N2O4 gas. That's another important information you are given. You know why this happens actually? Maybe you remember you learned that one in even inorganic chemistry. Even in bonding, you learn it, because once you draw the structure of NO2, it's this way, double bond O and dative covalent bond O. But nitrogen, there should be 5 valence electrons, 2 enol in bonding and another 2 enol in bonding because it's dative bond, and 1 electron here. These type of molecules are known as odd electron molecules. But once you consider odd electron molecules, then it's quite unstable. Here, single electron available. That's why it is unstable, or we can say less stable. Because of that, what happened? This type of, two NO2 molecules undergo dimerization. These two molecules now equally share these two unpaired electrons and have a new sigma bonds. Once it forms a new sigma bond, it becomes N2O4. Therefore, NO2 molecule can undergo dimerization to form then N2O4. Normally, in equilibrium, we will learn like there is equilibrium, 2NO2, N2O4, equilibrium is there. But according to this question, we can assume that here it's given actually, this is completely converted into N2O4. That means whatever NO2 form, it doesn't stay as NO2, it completely converted into N2O4. That is the information you are given, right? Then, as I said, we need initial moles of NO and O2. To find out the initial mole, what you are given, temperature, pressure, those things given. Here in the question, actually, 250 milliliter flask, other flask is 100 milliliter flask. But they say NO in the larger flask. Which one is the larger one? 250 milliliter. So to find out this, what we have to do to NO, apply PV equals nRT and then subject number of moles. It's the pressure. The pressure of this gas is given 1.5 atm, but better you convert that into SI. You know what to do? We multiply this by 1.013 10 to the power of 5. It's Newton per square meter or Pascal. Volume given 250, but that is in milliliter. You should convert that into cubic meter. And the R value then 8.314 joules per moles per Kelvin. And temperature is available 300 Kelvin. So once you simplify the units, you will end up with number of moles. Yes, number of moles, then mole. MOL is the unit for this one. So once we simplify this one, you will end up with this type of value. Earlier I did this one and then got this value. This is to save our time. 0.0152 mole. That's the number of initial moles of NO available. We have 0.0152. 0.0152. Then we need to find out the number of moles of oxygen gas, but we can do the same thing because same data available, volume, pressure, temperature, those are available. So to oxygen gas, then you can apply PV equals nRT again. But the number of moles of this will be pressure, in the other vessel mean 100 milliliter. Pressure of this one given 2 atm, but this should be again converted into Pascal or Newton per square meter. That is multiplied by the volume 100 milliliter, but that should be converted into cubic meter. R value SI at 0.314 joules per moles per Kelvin, and temperature given 300 Kelvin. So once you simplify this, you end up with like 0.0081 mole. Let's take up to 4 decimal places. So that's the initial mole of oxygen gas available. It's 0.001. Not 181. So we don't have these things initially. NO2 not available initially. That is a product. Now we end up with initial moles of both reactant. Then the next step is to identify the limiting reagent, because otherwise we can't predict what amount of NO2 formed here. Let's go to finding the limiting reagent. Right. Since initial moles are available, actually this is initial moles of NO and O2. Then we can go through reacting moles and then the remaining moles. Since these two available, we should be able to find out which one is limiting reagent. 0.0152, here 0.0081. This is actually chemical calculation part. Most of you think that this one is limiting reagent. The reason for that, this amount is less than this one. So if you have less amount, then most probably that will be finished first. But it doesn't happen always, right? Because we have to think about the stoichiometry. It is 1:2. Therefore, we have to be careful. Okay, but I assume this one is limiting reagent, NO. If that is limiting reagent, it should be fully reacted. Then remaining mole, reacting mole should be whatever initially available. Then reacting mole of oxygen will be half of that. 2 moles react with 1 mole of O2. Then what about the half of that? It should be 0.0 against 0. 15 divided by 2, 7, it's 14 and 16. 0.0076 should be the reacting mole of O2 with 0.0152. Then my question is, do we have 0.0076? Of course, available, more than that. Then my assumption is correct. My assumption is correct. Here the limiting reagent is nitric oxide. Those who assume oxygen as limiting reagent, then you can do the same thing. Remaining 0, reacting will be this, then 2 times of that and see whether it is available. But no, because 2 into 1, 2, 2 into 8, 16, 162 should be available. But what is available? 152. You can understand it. So therefore, definitely oxygen is not limiting reagent. This one is the limiting reagent, NO. Right, now we take the remaining moles of oxygen. It's should be 5 here, 7, 7, it's 0 and 0, 0. Yes, 0.005 moles of oxygen remain after the completion of reaction. Now we go to NO2. NO2 will be predicted again based on this limiting reagent. Limiting reagent reacting mole this 2:2, 1:1, then same number of moles should be 4. So the number of moles of NO2 formed should be 0.0152. But there's a question here. We don't have NO2. We don't have NO2 because this is completely converted into what? Into O4. Actually, once I follow the the stoichiometry here, 2 produce 1, then this should produce half of that. This should produce half of that. So what is half of that? It's 0.0076. That's the mole of NO2, N2O4 available in the system. So finally, you don't have NO2, but you have 0.0076 moles of N2O4. This is the situation in this vessel, in this system, after the completion of reaction, right? Then according to the question, next what do we have? Here you can see it's given like this. The gases are mixed by opening the stopcock. After the end of the reaction, the flasks are cooled. Earlier, until this, then the temperature is 300 Kelvin, but now we take that one to 220 Kelvin. That means we reduce the temperature. Once you reduce the temperature, there is one important thing given. At the beginning, it's given at 262. 262. Ne? We brought back to, I think, 262. 262. Then at 262, or the temperature less than that, the physical state of N2O4 becomes solid. It's given at the beginning. At 262 Kelvin, N2O4 is a solid. Then this is a solid at that condition. Only one gas available, it is oxygen only. And the number of moles of that gas available, 510 to the power of minus 4 moles. Okay. Don't take N2O4 gas at even this low temperature. It is not then gas. It should be then solid. It's given. Then the question is this, neglecting the vapor pressure of the dimer means N2O4. Find out the pressure and composition of the gas remaining at this one. So then composition we already got. It's 0.005 O2 available. But they asked to find out the pressure. To find out the pressure, what we need, again to final system, we apply PV equals nRT. We apply PV equals nRT. So pressure will be like number of moles, 510 to the power of minus 4 moles. Right? I think you noticed that I took only this number of moles. I didn't take this one. The reason for that one, N2O4, it's not a gas. We apply PV equals nRT only for the gases. N2O4 is not the gas. So therefore, we don't apply that one. So we take only oxygen gas, 8.314, that's the R value. And temperature now, it's 262 should be. Is that what is given in the question? 220 given. Dimer solidifies at 262. Means 220 Kelvin given, but it's okay. Even 220, it should be solid because it dimerizes at 262. Then any temperature less than that should be then this is 220 given. Any temperature below 262 should be again solid. Then we use 220, the value given. Right, nRT divided by P, pressure. That's a question, divided by volume. Now what's the volume? These two vessels are connected. Earlier, NO is one vessel, 250 milliliter. Oxygen is another vessel, 100 milliliter. Thereafter, we connect them. The gases mix freely. Now we can take both of these two as the one system, same system. Then 250 plus 100, it should be 350 milliliter. But I should convert that into cubic meter, the SI one. So this is the correct substitution pressure. Thereafter, we can find out the pressure, the answer for the question by simplifying this one. Minus 4 cancelled out. You get 10 to the power of minus 2 becomes then plus 2. Once you simplify these things, you get 26.128. But once we simplify the 10 to the powers, minus 2 cancel, we take it up, it becomes plus 2. The unit should be then Pascal or Newton per square meter. That's the SI square. Or in other words, you can say it's 2.6128 into 10 to the power of 3 Pascal. This is the answer for the pressure of the system, final pressure of the system. Then composition of oxygen gas is also there. You can say the number of moles of NO available, 0. Number of moles of O2 available at the end, it's 510 to the power of -4 moles. They ask composition of gases, then N2O4 is not gas. Therefore, you can give the answer for that question like this. Thereafter, they ask the pressure of the system. Then this will be the answer for that question. Got it? I hope you understood that one. Let's meet with another question.